Hi, in this video we're going to be talking about using diagonalization of matrices to solve linear difference equations, specifically homogeneous ones. And our primary example that we're going to be using is the Fibonacci numbers. So recall that the Fibonacci numbers, first few are right here, they're defined by this recurrence relation, f sub n is equal to the sum of the previous two terms, and then we set the 0th term to 0 and the first term to 1. Okay, and here's just a reminder of our previous way of doing this. We have the auxiliary equation is r squared minus r minus 1 equal to 0, and the roots of that are given by the quadratic formula, 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. I'm going to refer to those as a and b. Just to note, this number right here is the golden ratio, and usually it is denoted by phi, the Greek letter phi, and this number over here is usually denoted by phi prime. In order to avoid raising phi with a prime in it to a power, I'm just going to use a and b. Okay, so some properties of a and b that we'll need are, first of all, the product of a and b is -1. There's two ways to see this. First of all, you could just take this fraction, multiply by that fraction. Multiplying the numerators together would give you a difference of squares. You'd have 1 squared minus the square root of 5 squared. So that's the same thing as 1 minus 5, which is -4. So the numerator of a times b is -4. And the denominator is going to be 2 times 2, which is +4. -4 divided by +4 is -1. A simpler way to see that their product is -1 is whenever you take the product of two roots of a quadratic, you're going to get the constant term, at least if the quadratic is monic. In other words, if the leading coefficient is 1, then the product of the two roots will be the constant term, which is -1 in this case. Okay. Another property that we can see just by looking at a and b is if we subtract them, if we do this one minus this one, a minus b, then the ones here are going to cancel out, or really the 1/2 are going to cancel out, and it's going to leave us with root 5 over 2 minus negative root 5 over 2, and that's just root 5 over 2 plus root 5 over 2, which is root 5. So their difference is just the square root of 5. So we'll use that later. Okay, so previous way of doing this looks like this. We know that the general solution is a constant times a to the n plus a constant times b to the n. Remember, a to the n and b to the n are linearly independent solutions to this recurrence relation right here. So a general solution to the recurrence relation is a linear combination of those two solutions. So now we're going to take this and plug in n equals 0 and n equals 1 to account for our initial conditions here. So when we plug in n equals 0 into this equation right here, we get f sub 0 on the left side, and on the right side we get c1 a to the 0 plus c2 b to the 0, and we know that that should be set equal to 0 because f0 is 0. Okay, simplifying this, a to the 0 is 1, b to the 0 is 1, so this is just c1 plus c2 equals 0. Another way of saying that is c2 equals negative c1. Okay, I'm now going to take that knowledge that c2 is equal to negative c1, and I'm going to say this is c1 when I plug in n equals 1, f1 equals c1 a to the 1 minus c1 b to the 1. Saying minus c1 is the same thing as saying plus c2. Okay, and I'm setting that equal to 1 because f sub 1 is 1. And reading this off, we can factor out the c1 and say c1 times the difference of a and b is equal to 1. And here I'm using the fact that the difference of a and b is the square root of 5 to say that c1 is 1 over that difference, which is 1 over the square root of 5. Once we know that c1 is 1 over the square root of 5, then c2 is just the opposite. So c2 is -1 over the square root of 5. And now we can actually write our answer down. The formula for the Fibonacci sequence is given right here. as 1 over the square root of 5, that's our C1, times a to the n minus 1 over the square root of 5, so that's plus C2, times b to the n. Now we're going to find that exact same formula in a different way, using diagonalization of a matrix. So we're going to start out by looking at this formula for the Fibonacci sequence. F sub n is equal to f sub n minus 2 plus f sub n minus 1. And I'm going to note that the coefficients of these two are 1s. And I'm also going to write down a very similar equation. F sub n minus 1 is equal to, well, in this case, I'm going to use f sub n minus 1 on the right side, so I'm just going to say it's 0 of these plus 1 of those. So f sub n minus 1 is equal to 1 times itself. Okay, so that's a silly looking equation, but it's convenient because now I have the exact same two terms that I'm using on the right sides of these equations, and the left side I can think about a column vector, f sub n minus 1 and f sub n, and I can write these coefficients 0, 1, 1, 1 in a matrix and say this matrix times f sub n minus 2, the first variable here, and f sub n minus 1, the second variable here, is equal to f sub n minus 1 f sub n as a column vector. Okay, and this works for any n greater than or equal to 2, just like this works for any n greater than or equal to 2. And now I'm going to call this matrix here F. So let's look at what we can do with F. First of all, because this works for any n greater than or equal to 2, I can take the first instance where this works, and I can say f multiplied by the 0th in the first term. So this is plugging in n equals 2. So the 0th term of the Fibonacci sequence is 0, and the first term is 1. And doing this should shift up and give us the first term and the second term. So the first and the second term are right there, term 1 and term 2. And similarly, I could find the third, so I'll say the term 2 and term 3, so f sub 2 and f sub 3, by doing f times 1, 1. So f times this. Okay? So just in general, I want to think about f sub n minus 1, f sub n. This is f applied to this vector. And I want to think about that as, so this vector itself is f times the next smaller one down. So I'm just reducing the indices here by 1 again. Okay, and then I can do that again. So this matrix right here, or this column vector, is itself f times f sub n minus 4, f sub n minus 5. Oops, f sub n minus 3. All right, and the idea is I can keep doing this until I get all the way down to f sub 0, f sub 1. This is 0 and 1 right here. Okay, how many times do I have to do that? Well, each time I put an f down there, I'm allowed to subtract 1 off of this bottom index. So I have 1 f here, and I subtracted 1. I have 2 f's here, and I've subtracted 2. 3 f's here, I've subtracted 3. I want that bottom index to match this one. I want this to be F0, F1. So I'm going to try to put this vector in there. And to do that, I have to subtract off n minus 1 from this. So if I have n minus 1 factors of this matrix F, and I apply it to this, F0, F1, then I get back to this column vector. All right, and just to note, this is the same thing as writing this. Okay, so I'm going to record that information right here. F sub n minus 1, F sub n is equal to the matrix F raised to the power n minus 1 times the vector 0, 1. All right, so we know that diagonalization helps us raise matrices to powers, so let's go ahead and try to use that to simplify this F to the n minus 1. Our goal now is to find matrices D and P, so D is diagonal and P is invertible, so that F is equal to P D P inverse, and so then we can write F to this power is equal to P times D to that power times P inverse, because all the intermediate P and P inverses will cancel. Okay, so the characteristic equation for this, we're going to do F minus lambda I, just like we always do. Take the determinant of that and set it equal to 0. So I'm subtracting lambda off of the diagonal entries for F. So that should be a 1. So we have this right here. And then the determinant of a 2 by 2 matrix is the product of the main diagonal entries minus the product of the off diagonal entries. And so that's this times this minus this times this. And negative lambda times negative lambda is going to give us positive lambda squared. Negative lambda times 1 is going to be minus lambda. And then we have minus 1 on the end. Lambda squared minus lambda minus 1 equals 0 is the characteristic equation. And I just want to point out that that is essentially the same thing as our auxiliary equation for the exact same recurrence relation that we're using for this. That is not a coincidence. That will always happen. All right. So at this point, we know that the roots of this characteristic polynomial are going to be the eigenvalues of our matrix F. And so A and B, these same roots that we had over here, are exactly the eigenvalues of F. So let's try to find their corresponding eigenvectors. So I have A plugged in for lambda here into this matrix. And I'm applying it to a vector, and I'm getting 0. So I want to find a non-zero vector v, so that this applied to v is going to be equal to 0. And same thing for b over here. Okay, so I'm trying to find a u and a v so that I get these two equations satisfied. And I'm going to use the same trick that I used in the last video, where I know that these two rows are multiples of each other, even though they don't really look like they are. A is some specific number that has weird rules for multiplying it. And it turns out if you multiply this second row by negative A times 1 minus A is going to be equal to 1. Okay, so negative A times 1 minus A will be equal to 1 if you move that to the other side. And so even though it doesn't look like it is right now, it's always going to be the case that this is not invertible. And for a 2 by 2 matrix, that means that the two rows are multiples of each other. Okay, so when I'm row reducing this, I'm just going to zero out the second row, not even worry about how I'm combining the rows to actually do that cancelization. Just zeroing out the second row. And I'm going to do that here as well. Okay, and the idea is once we do this, even without augmenting this with zeros and solving for a basis for the null space of this matrix, F minus lambda I, we can still point out an eigenvector of this. So I want some top coordinate and bottom coordinate so that the top coordinate times negative a plus the bottom coordinate times 1 is equal to 0. Okay, and the bottom coordinate of the result of this will automatically be 0 because I have the 0 vector here, or the 0 row here. So as long as the top coordinate times negative a plus the bottom coordinate times 1 of this vector is equal to 0, then this product will be 0. So I can do that by just setting the top coordinate to 1 and the bottom coordinate to a. Okay. The way I'm thinking about this is I'm dotting this vector with this vector, if you're familiar with dot products. And in order for that dot product to be 0, I need this vector to be perpendicular to that vector. Okay? And the way to find a vector that's perpendicular to another vector, if they're both in R2, is to just switch the coordinates and negate one. Okay? So we've switched, the first one is negative a, the second one is 1. We've switched them, and I've negated the negative a back to positive a. Okay? So 1a with this matrix multiplied by it is going to give us the 0 vector. Okay, very similar over here. 1b is the eigenvector that we want for this matrix. Okay, and again, I meant to put zeros in this second row. Okay, so we have our v and our u, and v is an eigenvector with eigenvalue a, and u is an eigenvector with eigenvalue b, and that means I can find my d and my p. So d is the diagonal matrix with just the eigenvalues along the diagonal, and p is the matrix with columns which are the eigenvectors. Okay, and remember 1a was the eigenvector corresponding to a. Those are both in the first column. 1b is the eigenvector corresponding to eigenvalue b. Those are both in the second column. The order matters. Okay, once I have p, I know my diagonalization, but I want to find p inverse because we're going to need it for this problem anyway. So to find p inverse, you need to switch the entries on the main diagonal. So this 1b became b1. You need to negate the entries in the off diagonal. So negative a and negative 1. And then on the outside, we're dividing by the determinant of p. The determinant of p is 1 times b minus 1 times a. In other words, b minus a. And remember, b minus a, well, it's just the opposite of this, and so it's just negative square root of 5. So dividing by b minus a is dividing by negative square root of 5. So I have negative 1 over the square root of 5 there. Okay, and now I'm just distributing the negative sign in to the matrix, so I have positive 1 over the square root of 5, and then all of these signs got flipped. We're now going to use our matrices D, P, and P inverse that we've just found to simplify this expression f sub n minus 1, f sub n equals f to the n minus 1 times the vector 0, 1 that we had from over here. Okay, so I'm going to replace f to the n minus 1 with this equivalent form, p d to the n minus 1 times p inverse, and I'm going to multiply this by the vector 0, 1. Okay, so p is here, d to the n minus 1. Because d is diagonal, I'm just raising the diagonal entries to the n minus 1 power. And then p inverse, remember, was this matrix times 1 over the square root of 5, and I've just pulled the 1 over the square root of 5 all the way out to the left. Constants always commute with matrix multiplication. Okay, so I'm now going to do this one at a time. So I'm going to multiply this rightmost matrix by the vector. And when I do that, because this is just the second standard basis vector, I'm just going to get the second column of this matrix, 1, negative 1. So this negative b and a, I can ignore them. One thing to note is if I had chosen to simplify this, in other words, if I had chosen to simplify f to the n minus 1 and get what it was equal to, I would have had to deal with that column, and this way I can avoid it because I only care about what happens to this one vector. Okay, once we have that, we have this second column, 1, negative 1. Then I'm going to multiply this matrix in, and that's just going to multiply the first entry by a to the n minus 1, and it's going to multiply the second entry by b to the n minus 1. Okay, so we have a to the n minus 1 and negative b to the n minus 1. And now I'm going to multiply p into this. And so the top entry is just going to be 1 times the first plus 1 times the second. In other words, it's just a to the n minus 1 minus b to the n minus 1. But it turns out I don't care about this top entry. The main thing I care about is the bottom entry, which is just the nth Fibonacci term, f sub n. Okay, so that's going to come from a times this top term. So a times a to the n minus 1 is just a to the n. And we're going to add on b times negative b to the n minus 1. That's just minus b to the n. Okay, so just to note, these two terms right here, they are consecutive terms of a sequence. And notice that one of them looks like the nth term in a sequence, and the other one looks like the n minus first term in a sequence. In other words, if this is a function of n, then this should be that function with n minus 1 replacing n. And that is the case here. Okay, so our bottom entry, f sub n, of this column vector is 1 over the square root of 5 times a to the n minus b to the n. In other words, f sub n is 1 over the square root of 5 times a to the n minus 1 over the square root of 5 b to the n, which is the exact same answer that we got before. Now I want to take a look at this example that we had before of a homogeneous linear difference equation whose auxiliary equation had a multiple root. So specifically it's 2 with multiplicity 2. And remember, the result that we got before was one of the solutions was 2 to the n, and another linearly independent solution was n times 2 to the n. And so our general solution is c1 times 2 to the n plus c2 times n times 2 to the n. And you might be curious, how might we get this n if we're doing this with diagonalization instead? And, well, there's a problem that arises. So let's take a look at this system of equations that we get. So this is just like before. A sub n is negative 4 times a sub n minus 2 plus 4 times a sub n minus 1. That's just rearranging this to solve for a sub n. And we want to say that a sub n minus 1 is 0 times a sub n minus 2 plus 1 times a sub n minus 1. We can then turn this into this matrix equation. So this column vector is this matrix of coefficients times this column vector. Okay, and this works for any n greater than or equal to 2. So we're going to have this matrix A, which is just this matrix of coefficients, just like before. Okay, so let's find the eigenvalues of A. The eigenvalues of A are 2 with multiplicity 2 because the characteristic equation is exactly the same as the auxiliary equation over here. Okay, the eigenvector corresponding to lambda equals 2 is just this vector right here. So we can do the same trick as before. We have this right here, a minus lambda I, where lambda equals 2 is plugged in. We get this matrix. And the second row is a multiple of the first row, so we can just zero it out. And we want a non-trivial solution to this, and so I'm going to swap the order of these two and negate one of them to find a perpendicular vector. Okay, so this negative 2 times 1 plus 1 times 2 is going to give us the 0 vector. Now, because we only have one vector here, we don't have enough to form a basis, so we don't have an eigenbasis for R2 with this matrix. Therefore, we cannot diagonalize the matrix, and it seems like we're stuck. However, there is something slightly different that you can do called Jordan decomposition. So it looks like this. So the idea is the same. S has to be invertible, and J, instead of being diagonal, It's diagonal with a little bit of a twist. It's hard to see the twist in the 2x2 case, but the idea is it's diagonal except for there's a 1 in some slightly off diagonal entries. So the diagonal that's right above the main diagonal has some 1s in it. And the idea here is we can still rewrite A in some other basis, and that basis has a matrix which the transformation is this J here. And J is a little bit nicer to use than A. So why is J nice? Well, because when we raise J to powers, we can predict the format. So J squared is J times itself. And when you multiply that out, you get 4404. And because I already know what the format is, I'm writing it like this. So this is 2 squared, and this is 2 times 2 to the 1, and this is 2 squared. When you multiply it by J again, what you're going to get is you're going to see that this just acts like a diagonal matrix in the sense that we just keep doubling it each time we multiply by another J. And this top right entry is going to do something weird. So we're going to double it. That's this 2 times here. So we double what was already there, and then we add 1 times 2 to this power right here. So the power of 2 that we had before was 1 smaller than these, so I had 2 to the 1 instead of 2 to the 2. And then when we double this, it becomes 2 to the 2, and then we're adding another 2 to the 2. So instead of 2 to the 2's, we have 3 2 to the 2's. Okay? That pattern is going to continue. If that's not believable based on what you see here, I suggest trying a couple more of these. Try to find up to J to the 5th and see that you believe the pattern yourself. The general pattern looks like this. These entries will be 2 to the n, and this entry will be n times 2 to the n minus 1. Okay? And hopefully now you can see that it's similar enough that we can still use this to find this solution here. Or in general, we can find something involving a linear combination of these things. All right. You don't need to know the Jordan decomposition. You don't need to know how to find S and S inverse for this class. And I'm just showing you this as a glimpse into the future for if you take another linear algebra class that's a little bit higher level than this one. All right, thank you for watching.